So here we discuss how a narrowband FM signal is generated. So first we will see what is a narrowband FM signal and why is it called narrowband FM, and how is it different from the wideband FM signal. And then after that, we'll see how we can generate a narrowband FM signal using the basic components that we already know from the knowledge of AM signal generation, right? So first of all, unlike AM, angle modulation is non-linear. So we'll see why is it called a non-linear modulation. So no properties of the Fourier transform can be directly applied for its bandwidth analysis. So let's first see what is the bandwidth of an FM signal. So as we have seen here, for the case of AM, if we just simply take the Fourier transform, we will know the range of frequencies involved in the AM signal, and so the bandwidth of the AM signal. But the issue with FM is that it is non-linear, so the Fourier transform cannot be applied to it because Fourier transform is for linear signals and systems. So, so we need to, use a different approach to obtain the bandwidth of an FM signal. So let's say we have a term 80, which is a time varying quantity, and its integral of the signal mt. So this is our message signal mt, and its integral is equal to 80. Now let's say we have an FM signal with an FM dash here. It's equal to a e raised to power the exponential e raised to power j omega ct plus kf80. So this 80 is substituted here. Kf, as we know, is the constant that is applied to convert the voltage 80 of the message signal into a phase, right? So you can see it appears in the phase of the exponential term. So the Kf converts voltage into phase angle. Now, this is equal to, remember, this exponential has two terms, the sine and cosine. So this is, if we simplify this further, so we have these two exponential terms where this is completely related to the carrier frequency, and this is related to the message signal, where 80, as we know, is the integral of the message mt. So now this signal is related to the FM signal through this expression. So we know that in the FM, the actual FM signal, we have the real part of this signal. So we have this cosine term. So that is why we will only, if we want to consider an FM signal, we need to see the real part of this signal. So why are we doing this analysis? It will become clearer as we move forward. So now let's expand the exponential term that we saw on the previous slide. So let's expand this exponential term, which is equal to this one. So what do we get? We get a 1 plus j kf80. So we are using the power series expansion. So here you can see that we have this a as it is. We have e raised to power j omega ct as it is, and we then expand this signal using the exponential power series. So that allows us to get these terms from the exponential signal. Now here you can see we have the nonlinear terms as well. We have square, we will have cube, and up to n. So this is the reason we were saying that FM is a nonlinear signal. So the real part of this signal would be equal to FM, which is equal to the cosine term. So which is equal to this signal, where we have the cosine terms. So the real part of this would give us, for example, we have over here so this J80, KF80 appears as it is. The real part is coming from e raised to power j omega ct. So we know that it has two terms, cos. If we open it through Euler's identity, we have cos omega ct plus J sine omega CT. So the real part of this is mentioned here, and that is equal to the FM signal. So this is the complete FM signal. The modulated wave, as we can see, what does it consist of? It has an unmodulated carrier plus amplitude modulated terms. So these terms, if you look closely, they are the same as an AM signal. So we have the carrier, and in place of the amplitude, we have a time varying quantity, which in this case depends upon the message signal. So we have an unmodulated carrier and then amplitude modulated terms that we can see here, right? The terms are dependent upon the square and cube of AT. Now, what we extract from the information up to now is that the signal AT, as we know, is integral of MT. So if MF, which is the Fourier transform of MT, is band limited to B, the integral property of Fourier transform tells us that AF would also be band limited to B. So the spectrum of A square T, because we have multiplication in the time domain, so in the frequency domain, we will have convolution. So the spectrum of A square T would be band limited to 2B, because convolution of this, which has a band width of B, and convolution of this term, which has a bandwidth of B, would be equal to 2B, right? So this is from the convolution property of Fourier transform. So this means the spectrum of A and T would be band limited to NB. So hence from this analysis, we can see the spectrum that of this signal, this FM signal, would consist of a very large bandwidth signals. So because it has A square, A up to AN, NT. So that means the spectrum of that signal is NB. So clearly the modulated signal is not band limited. It has infinite bandwidth and is not related to the modulating signal spectrum in any simple way. So in case of AM, the modulated AM signal was related in simple way to this message signal. But in this case, FM, it's not directly related. The bandwidth is not directly related to the message signal. In fact, we can see we are getting an infinite bandwidth. So although bandwidth of an FM wave is theoretically infinite, for practical signals, if we have a bounded AT, right? So KF80 will remain finite. So this term, KF80 that appears here as well, this will remain finite if AT is also finite, if it's bounded. So in that expression, the terms that have KF80 raised to power n, they decrease at a very quick rate, because in the denominator we have n factorial as well. So we can ignore the higher order terms. So we shall see that most of the modulated signal power resides in finite bandwidth. So there are two distinct possibilities in terms of bandwidths. From this discussion, we see we can have two types of FM signals. One is the narrowband FM and the other is the wideband FM. So unlike AM, angle modulations are nonlinear. We have established this fact. Nonlinear relationship between AT and phi t is evident from the terms that involve A and T, right? So when KF is very small, this KF80 would be much smaller than 1, right? So this can be seen from here. Where is KF80 coming from? It's coming from here. So if KF is small, then this KF80 would be much smaller than 1. So all higher order terms are negligible except for the first two. So in this expression, all these terms can be neglected because the KF80 is much smaller than 1. So the square would be even smaller and cube would be even smaller. And then we have a factorial term in the denominator as well, which makes these terms even more smaller. So only the first two terms can be considered. And so we get this as the resulting FM signal, where only the first two terms are considered. So if we look at this term, it's similar to an AM signal, except that instead of a cosine, we have a sine here, right? So rest of the signal looks like just like an AM signal. So that means the bandwidth of this signal will now directly depend upon KF80, right? So this approximation is a linear modulation that has an expression similar to that of an AM signal with message AT. So we are talking about this expression. It has a bandwidth that is dependent upon AT. So it looks like a full AM signal. So because the bandwidth of AT is B, as we discussed previously, the bandwidth of the FM signal would be 2B. An FM signal where we have ignored the higher order terms has a bandwidth of 2B, which is similar to an AM signal. So this is according to the frequency shifting property, because we have AT multiplied by sine omega CT. So we will have a carrier omega C, and then we will have some an upper sideband and a lower sideband that makes the total bandwidth equal to 2B. For this reason, the FM signal for the case of KF 80 much less than 1 is called a narrowband FM, or it's in short, it's called NBFM. We can have a narrowband PM signal as well, where we can see instead of KF80, we have KPMT. So we know that in a phase modulated signal, the phase is directly dependent upon MT. In case of FM, the phase is directly dependent upon the integral of MT. So this is the difference. Now, there are two ways of generating FMs. Now, let's come to the point where we will discuss the generation of FM. So we have seen the FM and PM signals, the narrowband ones, right? So the discussion on wideband FM generation is in another video that you can see. So we first described the narrowband FM generator that is utilized in the indirect FM generation of wideband as well. So first we'll see narrowband FM generator. The same generator would be used, as we'll see in another video, it will be used to generate wideband angle modulated signal, or FM or PM. So for narrowband FM and PM signals that satisfy this condition, KF80 is much less than 1, or KPMT is much less than 1. We have these expressions, so they represent the narrowband FM and PM signals. So we just have to implement them based on the knowledge that we have from the AM wave, the knowledge of the circuit we have for the generation of AM wave. So in this slide, we can see we can use a double sideband suppressed carrier modulator to generate a narrowband FM signal. So we have MT at the input, we take the integral, we get 80. We pass this through we give this 80 as input to a DSB-SC modulator. The other input to the modulator comes from an oscillator that has initial frequency or initial value of A cos omega CT. We pass it through a phase shifter and we get minus A sine omega CT. When we pass these two inputs to the DSB-SC, what we get at the output is an AM signal where the amplitude is now this, and we have sine omega CT. And there is a summation, because if you see, we have generated this signal through DSB-SC. Now we have to add this carrier as well, because it looks like a full AM signal. So in order to add this carrier, we have an addition, summation, after which we will get the desired narrowband FM signal. Same process is followed for a narrowband PM signal, except that to the DSB-SC modulator, the input given is now MT instead of the integral of MT. Rest, the other input is minus A sine omega CT. At the output, we get an AM signal. To make it a full AM or to convert it to a narrowband PM, we add this carrier as well. And this is how we are able to generate a narrowband FM signal. So first we discussed the bandwidth of an FM signal, which gives us the information that we will have two types of angle modulated signals. One is narrowband and one is wideband. Then we saw that we can generate a narrowband FM or PM using the same modulator that we have used for amplitude modulation, right? So this is for narrowband signals. For wideband FM, we refer to the other video that is available on the channel.